È un piacere poter avere questa sera il professor Mukunda dell'Indian Institute of Science, però prima di presentare Mukunda devo dire che devo ringraziare Antonio Gargano per l'efficienza con cui ha tradotto questo manoscritto della conferenza del professor Mukunda e che ha avuto ieri sera scritto a mano e quindi fra l'altro perfino illeggibile. Credo che ha fatto letteralmente dei miracoli. Per quanto riguarda il professor Mukunda, in questo momento lui è direttore dell'Indian Institute, del centro per studi teorici dell'Indian Institute of Science, e è un piacere dire che fa parte di quella felice tradizione della fisica matematica indiana che ha avuto esponenti come Bose, molti di voi sapranno della statistica di Einstein-Bose, Baba, Gupta, Chandrasekhar, Harishchandra e ovviamente Sudarshan. Mukunda è stato studente di Sudarshan a Rochester e poi, come tutti i ricercatori di un certo livello, ha fatto il suo training a Princeton. Di recente ha avuto il premio del governo dell'India per le scienze fisiche, infatti nel 1980, che si chiama il Bhatnagar, ed è un premio che viene dato agli scienziati indiani che si distinguono nel campo delle scienze, in particolare questa era per le scienze fisiche. Di Mukunda devo dire che io ho avuto il piacere di collaborare e collaboro con lui ancora su molte questioni di fisica matematica, ma una delle sue più grandi doti è la lucidità, diciamo, nei problemi di fisica matematica, nel portare avanti i vari aspetti e i dettagli minuti. Una credo dei grossi contributi degli ultimi tempi è stato sicuramente quello che ai fisici è noto come le nuove equazioni di Dirac. Dirac stesso aveva scritto queste equazioni e c'era un problema che lui non era riuscito a risolvere, e di recente Mukunda, Sudarshan e Chang hanno risolto questa difficoltà e Dirac stesso ne ha fatto un apprezzamento ufficiale nel suo ultimo compleanno, nel Festschrift. Quindi è con molto piacere che abbiamo qua Mukunda stasera a parlarci dello stile della matematica nella fisica contemporanea. Fra i suoi contributi dovrei citare i contributi in meccanica classica, l'analisi del cosiddetto gruppo SL2 e recentemente importanti contributi nel campo dell'ottica. Quindi credo che a questo punto I must give you the microphone and ask you to speak. Perhaps I can add something. Mukunda is going Mukunda farà la sua conferenza essenzialmente seguendo il testo che ci avete in italiano e quindi io non tradurrò in simultanea come abbiamo fatto altre volte. Quello che faremo alla fine, se possiamo forse interrompere ogni tanto, in modo che se ci sono, ma forse le domande è preferibile farle alla fine, quindi lo facciamo leggere o comunque andare percorrere la sua conferenza e dopodiché, se ci abbiamo del tempo, forse possiamo dedicare un po' di spazio alla discussione. Please.
Well, sound is on.
It should be on, isn't it? Yeah.
Sometime later I shall request you to translate from Italian into English all that you have said now. Some years ago my teacher Sudarshan told me, when you are introduced at a lecture, if somebody says very nice things about you, even if they are not true, don't contradict them. So I shall not contradict what you have said, because you have mentioned the names of Bose and Bhabha and Saha and Harish Chandra in this context, and I certainly feel very small when that is done. Let me begin by expressing my deep appreciation and thanks to the Italian Institute of Philosophical Studies for inviting me to give this talk. It has made me work and think a little hard, and if you had not invited me, I would not have put in this effort. I am, of course, well aware that many truly distinguished persons have spoken to you in the past and will speak to you in the future on subjects quite similar to mine. It is therefore with a true sense of humility that I have prepared this talk. Please accept what I have to say as the thoughts of a physicist who constantly struggles to comprehend the works of masters. The title in English is The Mathematical Style of Modern Physics, and my colleagues have tried to translate this into Italian as closely as possible. Physics is the science of measurement and change, a subject in which we isolate particular natural phenomena far enough to make precise observations and measurements, then construct in our minds models and theories to explain them and maybe predict new phenomena. However, our unaided human senses are limited in their powers of observation, and as we explore phenomena far removed from our own scale, we have to rely more and more on refined instruments of observation. These instruments are, of course, the results of previously studied phenomena, and so we may think of them more or less as extensions of ourselves. The important point that we must bear in mind as we look at processes taking place either at the microscopic level or at the macroscopic level, that is, much smaller than ourselves or much bigger than ourselves, the point that we must remember is that the intuition which we gather from daily experiences is often useless as a guide to understanding these phenomena. So, in place of ordinary intuition, we have to develop and rely on mathematics as our guide and make it into a sixth sense in addition to what nature has given us already. Anything to say? Mathematics is, of course, used and very effectively used also to describe physics on the human scale. And in this context, one should not underestimate the difficulties faced in the past in the creation of new concepts. I will give you an elementary example. To us today, the idea of acceleration, the rate of change of velocity with time, seems very easy to grasp. Whenever you think of an automobile, when the advertiser tells you what kind of engine it has, he will tell you that in so many seconds, the automobile will go from 0 kilometers per hour, let us say, to 100 kilometers per hour. So the idea of acceleration is there in everyday language. But it appears that it took many years for Galileo to arrive at the idea of acceleration and understand its importance and significance. I have read somewhere that it took him either 16 or 25 years, I do not remember which, to precisely define acceleration as we use it today. Apparently, at that time, it was at first not clear whether one should define acceleration as the rate of change of velocity with respect to distance or with respect to time. Be that as it may, there is no doubt that with the developments of general relativity and quantum theory in this century, the texture of theoretical physics has become unexpectedly different and abstract. This situation was very well described by P.A.M. Dirac when he wrote in the introduction to a famous paper in 1931 the following sentences. The steady progress of physics requires for its theoretical formulation a mathematics that gets continually more advanced. This is only natural and to be expected. What, however, was not expected by the scientific workers of the last century was the particular form that the line of advancement of the mathematics would take. Namely, it was expected that the mathematics would get more and more complicated, but would rest on a permanent basis of axioms and definitions. Actually, the modern physical developments have required a mathematics that continually shifts its foundations and gets more abstract. Non-Euclidean geometry and non-commutative algebra, which were at one time considered to be purely fictions of the mind and pastimes for logical thinkers, have now been found to be very necessary for the description of general facts of the physical world. It seems likely that this process of increasing abstraction will continue in the future, and that advance in physics is to be associated with a continual modification and generalization of the axioms at the base of the mathematics, rather than with a logical development of any one mathematical scheme on a fixed foundation. That's the end of the quotation. The only problem with Dirac is that the sentences are sometimes very long, and one has to keep track of the ideas. As part of this changing style in which mathematical structures are used in physical theories, I would today like to describe to you two sets of ideas. One is the increasing importance of the concept of symmetry and invariance. The other is the fascinating and often unavoidable use of in principle unobservable quantities in formulating physical theories. First, let me explain briefly the idea of symmetry. The most immediate sense in which we all appreciate this idea is at first in a static sense. We all know what it means to say that a particular object around us is highly symmetric. For example, you can think of a building with a beautiful geometrical structure, or of a well-developed crystal, or maybe a precious stone, a diamond. To say that an object is highly symmetric is to say that it presents the same appearance when seen from several different points of view. In a technical sense, this definition of symmetry is called the passive point of view. Put in a slightly different but equivalent way, we can say the symmetry of an object means that it presents the same appearance to us before and after application of certain geometrical transformations. This way of defining symmetry is called the active point of view. A geometrical transformation for any given object would be some definite combination of operations in space, like rotations, translations, and maybe reflections in space, and we apply such operations to an object, and after the application, it looks the same as it did before. There is a whole area of mathematics, group theory, and in particular, the theory of finite groups and discrete groups, which is the perfect language for the description of such static symmetry. And as you would know, the mathematical classification of the symmetry groups of crystals was perfected almost 100 years ago, I suppose, and is a standard branch of solid-state physics. However, for our present discussion, we have to go beyond this kind of symmetry. We have to indulge in some amount of abstraction. That is, we have to go from the concrete to the abstract, and we must learn to appreciate, starting from the concept of static symmetry of objects, the dynamic symmetries of processes taking place in time. In the analysis of phenomena that evolve in time, we use three basic ideas which are of equal importance, and this has been specially emphasized by the great physicist Wigner. These three ideas are the laws of motion or evolution, the choices of initial conditions that are allowed, and the symmetries of the laws of motion. I will consider only deterministic laws of motion here. That is, they are laws which tell us, given the state of a physical system at a certain time, that what we call the initial condition of the system, the laws tell us how the state changes in the course of time and the physical system evolves. Thus, the laws of motion allow us to determine possible sequences of states in time, or if you like, possible histories of a system. Each such history corresponds to one particular choice of initial condition. In this framework, a symmetry is an operation that leads us from one allowed historical sequence of states to another, generally different historical sequence of states for the system. Such a symmetry is dynamical in the sense that it describes a property of the equations of motion, equations of evolution of a system, and not of the initial conditions. In other words, what I try to say here is that by looking at the state of a physical system at one time, you will not be able to discover the symmetries that govern the system and its evolution. You have to follow the development of the system through time for various possible initial conditions, and then see if there is something systematic that can be found. So, symmetry in this sense acts on the solutions of equations and not on the objects themselves. This is why it is rather abstract. It is the equations that are preserved under a symmetry transformation, not a particular physical state. As I said just now, that makes symmetry in this sense more abstract and harder to see. I have written see in quotation. Is this the?
Yes.
Fine, because that was important. In this sense, it is that one says that the equations of Newton for classical dynamics are symmetric or preserved under the transformations of the Galilean group. In a similar sense, we say that the equations of Maxwell for electricity and magnetism are symmetric or preserved under the transformations of the Lorentz group. In both these cases, the equations of Newton and the equations of Maxwell, historically it is a fact that the equations were discovered first and an appreciation and understanding of all their symmetries came later. However, from the early part of this century, there has been a great change in this situation. It started with Poincaré, who made a very systematic analysis of all the symmetries of the Maxwell equations, the first full-scale use of symmetry in the sense of a dynamical symmetry. And this attitude, this way of analyzing symmetry and using it, was carried forward by relativity theory. First, it was with special relativity, and later it was with general relativity that the Einstein point of view came. This point of view says, let us use the requirements of symmetry as a guide in the construction of new theories. In the absence of any arguments based on symmetry, one would imagine that there is a great deal of freedom, almost uncontrollable, in the structure or in the construction of new theories. And the idea here is to insist that certain symmetries which have been discovered earlier are still relevant for new phenomena, and therefore they must be used as arguments to limit the theories that we would construct. It is in this sense that the general theory of relativity, at least as Einstein viewed and presented it originally, was to a very great extent determined in its detailed structure by the requirements of symmetry that he placed upon it. I can summarize this situation very briefly by saying that the concept of symmetry started as something describing laws of nature, then something limiting laws of nature, and today determining laws of nature, from description to limiting to determination. That is not in the text. The next most impressive example of this phenomenon, the powerful use of symmetry, was the discovery of the relativistic wave equation for the electron. It came by combining three elements: the structure of quantum mechanics, the requirement of symmetry with respect to special relativity, and the genius of Dirac. In this context, I would like to tell you a small story which I have not written in the text. Where are we? Here. In the Solvay conference of 1927, Dirac has written somewhere, Niels Bohr asked Dirac what he was thinking about and what he was working on at that time. And Dirac said that he was unhappy with the fact that there was no relativistic equation in quantum mechanics. And Bohr said, "Oh, but that problem has been solved. Klein and Gordon have constructed the equation, and what are you looking for?" And Dirac presumably wanted to explain the situation to Bohr, but then the bell rang and the coffee break was over and they all had to go back to the session. The problem that was bothering Dirac was that though there was a wave equation of Klein and Gordon, it did not have the general form which he himself had found all quantum mechanical equations must have. That is, there is a technical statement, the transformation theory of quantum mechanics dictates that quantum mechanical equations should have a certain form. And he had discovered it, therefore that requirement was very much uppermost in his mind. And it was that he insisted on maintaining. So it was by combining the requirements of, if you like, symmetry, structure of quantum mechanics itself, and symmetry with respect to special relativity that Dirac was able to solve this problem. Sorry if it's hard.
No, that's questo è un commento, pare che in qualche conferenza a Solvay, come sapete queste conferenze a Solvay furono più o meno dopo l'inizio del secolo, si tennero con una certa frequenza, erano incontri fra fisici, in particolare c'era Niels Bohr e Dirac, e Dirac parlando con Bohr diceva: c'è una cosa che ancora mi preoccupa, è questo fatto che non possediamo una teoria dell'elettrone che in un certo senso sia relativisticamente covariante e allo stesso tempo ovviamente tenga conto della meccanica quantistica. E Bohr gli ha detto: oh, ma questo è stato già risolto da Klein e da Gordon alcuni anni prima. Nel frattempo pare che, come sapete, in queste conferenze poi a un certo punto suona il campanello e si interrompe per andare a pigliare il caffè, per cui la discussione non poté continuare perché tutti quanti si alzano e vanno a pigliare il caffè. Però nel frattempo quello che preoccupava Dirac e quello che poi lo ha portato, che lo portò dopo a scoprire la cosiddetta famosa equazione di Dirac, era il fatto che non aveva le proprietà di trasformazione giuste. Cioè l'equazione di Klein-Gordon non aveva le proprietà di trasformazione giuste appropriate per la meccanica quantistica. Vorrei ricordare qua che le equazioni di Dirac sono quelle che portarono Dirac poi a prevedere l'esistenza del cosiddetto positrone, cioè della particella che ha gli stessi attributi dell'elettrone ma che ha carica positiva. Quindi questo è un altro dei tanti esempi in cui in un certo senso la matematica poi suggerisce che cosa uno deve aspettarsi in natura, e quindi la scoperta poi successiva, un paio, 2 o 3 anni dopo, del positrone fu una conferma, diciamo, di questa intuizione. Comunque, quindi questo è un esempio di quello che può fare la ricerca di un certo senso estetico, diciamo, no? Questo imporre simmetrie e invarianze su certe equazioni. I think I went beyond you.
No, you did it very well. This trend or this style, the overriding dependence on symmetry and invariance properties, continues to this day and fulfills something which Dirac wrote in 1930 in the introduction, in the preface to his book on quantum mechanics. And I would like to quote this small paragraph from there. The growth of the use of transformation theory, as applied first to relativity and later to the quantum theory, is the essence of the new method in theoretical physics. Further progress lies in the direction of making our equations invariant under wider and still wider transformations. Now there is a sentence here which I would have liked to include in the text, but now I shall read it in any case because it is relevant to some of the later things that I say. So I continue with what he said. The formulation of these laws requires the use of the mathematics of transformations. The important things in the world appear as the invariants of these transformations. The things we are immediately aware of are the relations of these near invariants to a certain frame of reference. So there is the point here about what is there in the mathematics that will ultimately be related to observable quantities. So let it go. So now I go back to my own text. The most important recent example of this trend is the discovery of gauge theory. It is technically called non-abelian gauge theory by Yang and Mills in 1954 and also by Ruth Shaw about the same time. It is a case comparable in many ways to the general theory of relativity, in the sense that one requires such a great degree of invariance under certain transformations that the equations of motion are essentially uniquely determined in their structure. Yang has described this situation in talks in recent times by saying that we have reached the stage where symmetry dictates interaction structure, the third stage. The importance of Yang-Mills type theory is that it is believed today that all the forces known in physics apart from gravitation can be described by such theories, making use, of course, of the framework of quantum mechanics. That is, today people expect that the forces of electromagnetism, radioactivity, and the strong nuclear force acting within the atom are all of them of the type of Yang-Mills theory. In this discussion of symmetry, one must be also honest and point out that in some respects, the laws of nature are less symmetric than one had originally imagined. Thus, I think you all know now that parity is not a symmetry of the weak interactions that cause radioactivity. What does this mean? If you imagine a possible series of events taking place, and then you imagine the mirror image of this series of events, under certain circumstances, the original series of events occurs in nature, but the mirror image does not occur in nature. This is the meaning of the statement that parity is not always a symmetry. This fact was experimentally shown by a famous team of experimenters in 1957. More recent times, the role of symmetry is a little bit more unusual. One often constructs physical theories which at the beginning have much more symmetry than you really expect to observe in the end. And then, after having put in more symmetry than necessary, you arrange the equations very carefully so that in an automatic or spontaneous way, the symmetry becomes less than before. It becomes reduced to the extent to which you want it to be reduced. This may appear to you at first sight as a strange thing to do, something which we should avoid at all costs, but there are very good and important technical reasons why one should proceed in this way. I just point these two examples to say that it is not true that we always talk of symmetry. We also do talk of broken symmetry in physics. But it is all done in a very controlled and well understood fashion, and it does not in any way reduce the importance of symmetry considerations in modern physics. From a practical point of view, the consequences of symmetry have been much more important in the context of quantum physics rather than in the classical context. And here I may just explain very briefly why this is so, though it is not in the text. The point is that in a classical context, a symmetry operation of a given system generally changes one state into a different state. However, in quantum physics, there is a new principle called the superposition principle, and as a result of that, there are many, many more states available in quantum physics than in classical physics. And for any symmetry that you choose, it is possible to find physical states which are not altered by that symmetry. So the point is that in classical physics, most states get changed by a symmetry, whereas in quantum physics, there are many important states that are unchanged by the same symmetry. However, it may not be out of place for me to mention here that even in the classical framework, we constantly try to understand this concept and related concepts in a better and a deeper way by constantly refining the mathematical methods that we use. This is an activity in which myself and my hosts and colleagues here are very much involved. This is, in a small way, an example of another statement of Dirac from 1931, and I quote, "The most powerful method of advance that can be suggested at present is to employ all the resources of pure mathematics in attempts to perfect and generalize the mathematical formalism that forms the existing basis of theoretical physics. After each success in this direction, to try to interpret the new mathematical features in terms of physical entities." I think already Professor Marmor referred, the most dramatic example of this was the positron theory.
So you understand Italian?
Yeah,
well.
right. Yes. Let me now turn to the second main idea I want to present in this talk: the use of apparently unobservable quantities in the construction of physical theories. This concept is actually quite closely related to the increasingly strong symmetry requirements that we place on physical theories, the point that I have just completed making. This point can probably be conveyed best to you by first giving a few examples and then making some comments. The examples go from the simple to the complex. The first example I want to take is from the field of classical optics. Imagine that in that context we say that the basic observable quantity of optics is the intensity of light at a given point of space at a given time. For example, if one takes a photograph in black and white, what one is making is a record of the intensity of light at various points on the film existing at the time that the photograph was made. So you have a record of the variation of light intensity over the photographic plate. If, for instance, you make a color photograph, all that you are doing is that you are recording the variation of light intensity separately at separate frequencies, but it is still a measurement and a record of intensity. Now, the fundamental theory of light in classical physics is given by Maxwell's equations for the electromagnetic field. These equations tell us how, from given initial data, initial state of electric and magnetic fields, these fields develop in the course of time. So, at the level of Maxwell's equations, the concept of state at a given time means values of the electric and magnetic fields at a given time, not just values of the intensity at a given time. Now, there is a difference because the intensity of light is essentially the square of the electric and magnetic fields. So, it is not true that suppose you are given the initial distribution of light intensity over a plane, let us say, it is not true that you can predict what the intensity of light will be at a later time or elsewhere on another plane. Provisionally, if we define intensity of light to be the only observable quantity in classical optics, then in order to see how intensity changes in time or in space and how it propagates, we are forced to introduce something called the two-point correlation function, and this is completely unobservable at this level. Of course, it is a matter of definition. We have agreed that intensity is the only quantity that is observable. We are unable to predict how intensity propagates in space and time. In order to predict how it behaves, we have to introduce an unobservable quantity. For this two-point correlation function, there are well-defined laws of propagation or evolution. Of course, they are derived in a straightforward way from Maxwell's equations. The physical meaning of the two-point function is that it tells you to what extent there is a correlation between the electric field at one point in space and the electric field at another point in space. Of course, you may take the times to be the same or to be different. From the mathematical point of view, it is similar to light intensity in the sense that it involves the electric field quadratically. But from the physical point of view, it is quite different from light intensity. So the essential distinction is that correlation function is deterministic, intensity is not. However, the correlation function is unobservable by agreement and only light intensity is observable. So this example of the use of an unobservable quantity is in a sense provisional, because once you say that you really understand Maxwell's equations, you are willing to work with them, and you rise to the level where you say that the individual electric and magnetic fields are observable, then of course the correlation function is observable. But within the restricted framework of classical optics, relying only on intensity measurements, this example illustrates the point I wanted to make. Oh yeah, did you want to say something?
No, I don't think.
Going too fast?
Okay.
My second example uses again electromagnetism, but now taking for granted the observability of the electric and magnetic fields at the classical level. In the mathematical description of electromagnetism, one often finds it convenient to express the basic fields, electric and magnetic fields, in terms of a more primitive object called a vector potential. But this is in principle not an observable quantity. This happens in this case because there is a symmetry, the idea that we have already discussed. It happens that in electromagnetism, there are transformations that change the vector potential but do not change the observable quantities, the electric and magnetic fields. For this reason, classically we say that the vector potential is not observable. In any case, in the classical theory, it is not very hard to write all the equations of electromagnetism interacting with matter directly in terms of the observable quantities alone, namely in terms of electric and magnetic fields. So it is possible in writing the basic equations to completely avoid the use of the vector potential. But the situation changes dramatically when one considers this situation in quantum mechanics. Suppose you consider a particle such as an electron whose motion is described according to the laws of quantum mechanics, and suppose it is moving in an electromagnetic field. In this case, to write the equations for such motion of the electron, it appears essential to use the vector potential, which we agreed was classically unobservable. We know of no simple way of writing the equation of motion for the electron without using the vector potential at all. If you wish to avoid using the vector potential, what happens is that one comes against the problem of non-local action. So it is only by using the vector potential that one can remain within the scheme of ideas of local actions. In quantum theory, unlike classical theory, it is very awkward and inconvenient to eliminate the unobservable vector potential compared to classical theory. As I say, one can in principle do so, and it has been done both in the context of classical relativity and in quantum theory, but then the theory gets very complicated and unwieldy, that is, not easy to work with. So there is a temptation to say one cannot live without the vector potential. To bring this story up to date, there are two things that I should mention, one written here and one not written here. In recent times, one has found that some very delicate properties of the vector potential, which cannot be expressed in terms of the classical electric and magnetic fields, become observable in quantum mechanics. This situation is described by Yang by saying that a complete description of the electromagnetic field lies somewhere in between the electric and magnetic fields and the complete vector potential. You need more than the electric and magnetic fields. You do not need all the properties of the vector potential, but somewhere in between. So this is an example of the use of unobservable quantities in physical theories in the interests of convenience and to satisfy the prejudice that one should have only local actions. The second example I just wanted to mention in this context is what Professor Marmor reminded me about after my discussion with him, and that is, again, of course, a work of Dirac. He has analyzed the peculiar properties of the vector potential in quantum mechanics and related it to what is called the theory of the magnetic monopole. This is an object which is apparently not yet observed, and therefore it is the most fantastic theory of its kind.
Forse questo andrebbe aggiunto effettivamente, quindi tenterò di tradurre e forse di dire anche qualcosa in più, come il mio solito. Nel 31 dire che si era posto il grosso problema che un po' riguardava tutti in quel momento, era la cosiddetta quantizzazione della carica elettrica. Non si riusciva a capire se e perché la carica elettrica dovesse essere quantizzata. Allora, l'analisi di Dirac di tutti i fondamenti della meccanica quantistica lo portarono a concludere che la possibile esistenza del monopolo sarebbe una carica magnetica, così come c'è una carica elettrica, non portava nessuna modifica nei principi della meccanica quantistica. E quindi lui disse, allora se questa possibilità c'è, molto probabilmente la natura ne avrà fatto uso. Quindi molto probabilmente questi monopoli esisteranno. E fra l'altro questo portava a risolvere il problema della quantizzazione della carica elettrica, cioè se i monopoli esistono in natura, allora la carica elettrica è quantizzata e c'ha il valore che uno normalmente osserva. Quindi questo postulare la possibile esistenza di una particella di cui uno può predire le caratteristiche.
My third example in this list of unobservable quantities belongs to general relativity and in a closely related form to non-abelian gauge theory of the Yang-Mills type. As I mentioned earlier, the original form in which general relativity was presented depended very heavily on the symmetries that were imposed on the basic equations. As I said, these requirements of symmetry were so powerful that they practically determined the structure of the equations of the theory. Of course, again, one should not underestimate the difficulties of this task. It took Einstein 11 years to do it. One considers events taking place in space and time, and one imagines describing the locations of events with the help of space and time coordinates. Of course, many other mathematical objects are assumed. The essential point for our present discussion is that one says one has the freedom to make a great deal of change in the choice of coordinates. For a given event, there is no intrinsic meaning to the space and time coordinates we associate with it, and therefore the equations of the theory must preserve their form under any kind of transformation of coordinates that you may make. So this is the condition of symmetry or invariance that is imposed on the theory. In this description, in the early version of general relativity, let us say, the space-time variables enter the basic equations. You cannot write the equations without them, but it is with the full understanding that they are not observable. By not observable, I mean it was understood that they do not have an intrinsic experimental meaning. Of course, in the development of the theory over the next decades, more and more refined mathematical tools were developed and learned by people, and those methods of mathematics were used to write the equations of general relativity in as pure a form as possible. By this we mean by eliminating completely the coordinates which were unobservable to begin with. Today, what people call this form of writing the equations of relativity is a coordinate-free and intrinsic description. That is, you get rid as much as possible of unobservable mathematical symbols. But still the problem remains. The problem now is what quantities which appear in the mathematical theory are to be regarded as physically observable quantities. And this apparently is a very, very subtle question. As far as I know, it appears that this problem has not yet been completely solved. Even in the current literature, there is a great deal of discussion on this subject. Incidentally, I must mention two things in this context. One is a statement of Einstein to Heisenberg. around 1925 and 1926 to the effect that when one constructs a physical theory, it is a part of the theory to say, it is part of the statements of the theory to make clear what quantities that are introduced in it are to be regarded as physically observable. This question is not something that can be decided from outside the theory, but is internal to the theory. A few months ago, you had a very distinguished visitor here, Professor Peter Bergman, who has devoted many years of research to understanding and clarifying this problem of finding what is it in general relativity that is observable and what are all the complete set of observable quantities. As I said earlier, this is a very subtle question. In the theories of the Yang-Mills type, non-abelian gauge theories, the situation is somewhat similar, though probably slightly easier to handle. In this case, one can state fairly precisely a condition with the help of which you will decide whether any given object in the theory, any mathematical object, is observable or not observable. The usual way of handling the Yang-Mills theory uses quantities which are explicitly agreed shall not be observable. But if you try to get rid of them from the theory and write your expressions, write all your equations in a new form using only those things which you agree can be observed, it introduces complexities which are similar to the one that I described in the context of electromagnetism. However, there is a basic mathematical difference which is expressed in the term non-abelian. Yang-Mills theory is intrinsically more complicated than electromagnetism, and it is much harder to get rid of the analog of the vector potential in Yang-Mills theory than in Maxwell's theory. So this third example is again a case where it is preferable and convenient to allow the appearance of unobservable quantities in physical theories. You are then, of course, stuck with the problem of later deciding what is observable and what is not observable. The problem does not disappear, it is just relegated to another position. The fourth and last example I would like to present to you in this theme is quantum mechanics itself. In some respects, the situation is similar to the first example I took from classical optics. The difference is that in the case of quantum mechanics, it is most likely that the state of affairs is already a final state rather than something provisional that may change. The conventional view of quantum mechanics for the present purposes is as follows. If you take an atomic system, there are many physical quantities associated with it, but they cannot all be measured simultaneously, or they cannot all be given numerical values simultaneously. Compared with the classical description of an atomic system, quantum mechanics says that there are definite limitations on the amount of information we can have about an atomic system at one time. For example, you might measure, this is the most familiar case, you may measure the energy or the position of an electron, in which case you have no information about its momentum, or you may measure the momentum and then you have no information about the position. If you measure each of them, you want to be able to say something about position and something about momentum, then there is only a limited accuracy within which one can make such measurements. Now, imagine that by some suitable measurements, you have acquired the maximum amount of information permitted by the theory about an atomic system at a certain time. That is, the theory prescribes the kinds of experiments you can do in principle, carry out such an experiment, find out all you can about one observable which you have chosen, and which is the maximum information that is permitted. Then, how is this information described in the theory? Quantum mechanics says this maximum information at a given time is to be represented in the mathematics by a symbol called the wave function. We also sometimes use the word state vector. Now, in comparing this with the situation in classical optics, you can imagine that this wave function is analogous to the use of electric and magnetic fields in the context of optics. What the basic equations of quantum mechanics tell us is how the wave function varies with time. So in quantum mechanics, state at a given time or initial condition means wave function at a given time. At this level, where one writes the equation of motion in quantum mechanics, we can say that quantum mechanics is deterministic. That is, in quantum theory, there is a definition of physical state. It's a mathematical definition, but the definition is such that there is an equation of motion that can be written. State at one time determines state at another time. However, the object that describes the state, the wave function, is itself not observable. And this I have underlined. From the maximum amount of information that you may get at one time, we construct the wave function at that time. Then the equation of motion in quantum mechanics tells us, in a definite and deterministic way, the value of the wave function at any later time. Once we have the wave function at the later time, the theory can tell you, if you make any given measurement at the later time, the theory will tell you the probability with which various results will emerge. So the point is that the basic observable quantities predicted by quantum mechanics are these probabilities. The probabilities, however, involve the wave function not by itself but quadratically. That is, again, I give you the analogy with the optics. In the case of classical optics, the Maxwell equations told you how electric and magnetic fields change in the course of time. However, intensity was the square of the electric field. It is very similar here. The equation of Schrödinger tells you how the wave function changes with time. However, the probabilities, which are the measured or observable quantities, involve the square of the wave function. In other words, exactly as in the optical case, if we were given the probabilities for various results of measurement at one time, there is no way to calculate what happens to the system later. There are no equations which tell you how probabilities change in time, because any such equation immediately brings in things other than probabilities, and those are not directly observable. So the evolution is for an unobservable wave function and not for observable probabilities. At least at present, there seems to be no way of avoiding the use of the wave function in formulating quantum mechanics. It, that is a wave function or something very much like it, has to be used so that one may be able to express all the laws of quantum mechanical phenomena in a deterministic way. Relating this to a comment which I made earlier, the use of the wave function is essential because there is the property of the superposition in quantum mechanics, which is another way of saying that quantum mechanical states are many, many more and much more rich than in classical mechanics. Did you want to say anything? I just continue.
Yes, go on.
So we have, by these examples, seen three ways in which we use unobservable quantities in physical theories. One, where the theory is in a provisional state, a state where we know that in the course of time, things which were previously thought to be unobservable will later be seen to be observable. So that is a situation not to be worried about. Another situation is where we use unobservable quantities because it is a matter of convenience. And often it is a matter of such great convenience that you feel that it is inevitable to use unobservable things. It would be possible in principle, but extremely complicated in practice to eliminate the unobservable quantities. So there it's a question of reality versus convenience, if you like. But the third and most important situation is where there seems to be no way to avoid the appearance of unobservable objects. Then it is no longer just a matter of convenience or words or discussion, but it is essential to work with such things. Maybe I should say that this increased use of unobservable quantities goes hand in hand with the increased use of symmetry, but it should be clear that since these are the two ideas I have tried to expose, they are, of course, very closely related. It has been said by somebody, and very wisely so, that every generation of physicists feels that the next generation is too mathematical. Well, why is this so, and why does physical theory get more and more abstract and mathematical as time goes on? By now you know that the master I admire most and study most is Dirac. So there is no better way for me to express the reason for this trend than to quote from him again from the preface to his book in 1930. So I quote here, "The methods of progress in theoretical physics have undergone a vast change during the present century. The classical tradition has been to consider the world to be an association of observable objects, particles, fluids, fields, etc., moving about according to definite laws of force, so that one could form a mental picture in space and time of the whole scheme. This led to a physics whose aim was to make assumptions about the mechanisms and forces connecting these observable objects to account for their behavior in the simplest possible way. It has become increasingly evident in recent times, however, that nature works on a different plan. Her fundamental laws do not govern the world as it appears in our mental picture in any very direct way, but instead they control a substratum of which we cannot form a mental picture without introducing irrelevancies." That is the end of the quotation, and I must mention that it was only after I was asked to give this talk and I thought about it and prepared this, that I came to appreciate the depth of meaning in this sentence where Dirac says that in classical physics, all one was dealing with were observable objects. When I studied this book on quantum mechanics, I just read this preface like you would read any other preface, but now I read it again and understood much more. It therefore becomes increasingly necessary to rely more and more on our mathematical sensibilities in trying to comprehend the developing physical picture of nature. The writings of Dirac that I have quoted to you express beautifully the style of the mathematics, and his works have contributed a great part of the content of the mathematics, the changing mathematics that underlies modern theoretical physics. Thank you very much. Can I have some more?
Credo che se ci sono delle domande possiamo avere una breve sezione di discussione, e siccome tutti quanti voi avete il testo credo che non sia difficile.
additional comments that you had wanted to make? It would be nice.
Ma come di consuetudine, diciamo, allora sarò costretto io a fare una domanda al professor Mukunda. La farò prima in italiano e poi la farò, forse potrei fare viceversa, così lui nel frattempo ci può pensare. I would like to ask you a question. This is very much in the tradition, because if nobody asks a question, then I am obliged to do it. And you have been talking about the role or the style of mathematics with respect to physics. Could you comment or just give a few sentences on the vice versa? What has been the role of physics with respect to mathematics? La domanda essenzialmente, il professor Mukunda ci ha parlato del ruolo della matematica nella fisica. Che cosa uno può dire del ruolo della fisica nella matematica?
Well, let me make a few notes and then
Sure.
answer. Okay. Well, first, when did you think of this question? Just now? Well, of course, we know that mathematics and physics have been very close together for many centuries. In the early centuries, the people who did one did the other also. The greatest examples were Newton and Leibniz and so on. In talking about this century and in the same period in which I have given these two main ideas in my talk, I would like to make a couple of observations. One, of course, is that physics has used very effectively mathematical tools that were prepared earlier or almost simultaneously. But there are a couple of examples where, if one studies the development of the physics very carefully, and these are fascinating examples, one realizes that even if the mathematics had not yet been created, for the needs of physics, a new mathematics would have been created. And this has happened a couple of times. I will give you two examples. One is the first paper of Heisenberg on quantum mechanics in the year 1925. Heisenberg asked the question, and in retrospect it's a very simple question. He said, if a quantity x is regarded as an observable in quantum mechanics, what do we mean by the square of x? Now, what was the context in which the question was asked? Earlier he had made the statement that the concept of position for an electron in an atom is not really well defined, it is not directly observable. We must replace the classical concept of position, which is a real number, by a square array. That is, an infinite set of numbers arranged in rows and columns. Having made this statement that the classical real number x should now be regarded as this strange mathematical object, he asked the question, classically we know what we mean by square of x. What do we mean by square of x in quantum mechanics? And he used the well-known Ritz combination law of frequencies to answer this question. What was the answer he got? He got an answer which told you the square of x is another similar pattern, another array. And by using the physical law of the Ritz combination law of frequencies, he was able to tell you how to compute the square of x from x, how to compute the new array from the old one. Now, Heisenberg did not know that this was already known to the mathematicians as a matrix and the multiplication of matrices. He mentioned his way of doing it to his senior, Max Born, who approximately a week or so after he had been told by Heisenberg what he had discovered, remembered that in his school days he had learnt about matrices from his teacher, and this was nothing but the algebra of matrices. But it is very clear that even if the idea of matrices had not been developed earlier as a part of mathematics, you can see very graphically that the Ritz combination law of frequencies of physics told Heisenberg essentially that he had to deal with a matrix. And if it was not already there in mathematics, the physicists would have invented the concept of matrices and all the properties that go with it. You want to try to translate? Then I give another example.
Beh, cercherò di tradurre in base a quello che mi ricordo, naturalmente. Beh, l'esempio è che effettivamente se uno va indietro a Newton e a Leibniz non è che ci fosse molta distinzione fra fisici e matematici. Beh, tutti quanti si ricordano, diciamo, il calcolo differenziale, per esempio, no? E la prima osservazione è che la fisica in un certo senso, fino a un certo punto ha usato la matematica che era stata già elaborata. Da un certo momento in poi ha cominciato a creare la matematica che serviva. Allora, l'esempio in particolare che il professor Mukunda cita è quello di Heisenberg con la meccanica quantistica. L'idea di sostituire alle osservabili classiche un quadrato di numeri, essenzialmente quello che chiamiamo matrice, diciamo. E la regola di composizione, cioè il modo con cui questi si moltiplicano, visto che Heisenberg non conosceva l'algebra delle matrici, l'ha ricavata dalla regola di composizione degli spettri, la cosiddetta regola di composizione di Ritz. Quindi qua è un esempio in cui è vero che i matematici conoscevano già l'algebra delle matrici, ma ciò nonostante è stata riscoperta, e questa volta riscoperta con delle regole di composizione che sono regole di composizione all'interno della fisica. E quindi il commento è che, per esempio, molto probabilmente l'algebra delle matrici sarebbe stata scoperta comunque, indipendentemente dai matematici. E poi c'è un secondo esempio che adesso sentiremo.
The next example. Yeah, the other example is actually even more familiar. It goes back to Dirac, who introduced the famous Dirac delta function as a very convenient tool to express all the formulas that one deals with in quantum mechanics. And that idea of the delta function led to two very fruitful things. One was a polemic by von Neumann against Dirac for introducing such things which he said were obviously mathematically nonsensical, but he went beyond making just such a statement. He wrote a beautiful book about his view of quantum mechanics. Much later, the theory of distributions was developed as a very nice and powerful tool in mathematics to make the idea of Dirac mathematically acceptable. So these examples show that even today, physics and physical problems do act very effectively as the sources and ideas of new mathematics. However, it is true that there is a divergence between the two. One tries to bridge it by constantly learning the language of well-educated people.
Il secondo esempio naturalmente non poteva che essere un esempio ispirato a Dirac, ed è la famosa funzione delta con cui gli studenti del terzo anno più o meno di fisica si trovano a combattere. Beh, questa funzione effettivamente non esiste come funzione. E von Neumann fu così irritato da questa funzione che decise di scrivere un libro sulla meccanica quantistica in cui evitava accuratamente di introdurre qualunque funzione cosiddetta funzione delta di Dirac. E poi Schwarz essenzialmente nel 45-46 ha fatto la cosiddetta teoria delle distribuzioni, e che adesso è un bellissimo capitolo della matematica che effettivamente è originato dalla delta di Dirac. Quindi c'è questo scambio spesso fra matematica e fisica, però uno deve dire che ci sono anche delle divergenze. Thank you.
Thank you.
Non so se ci sono altre domande.
I would like to ask you a similar question.
Yes.
Yes, I know that there has been progress in logics and mathematics due to the progress in quantum physics. I have heard of the logic, the quantum logics. I would like to know whether the developing of such logic based on physical problems could increase and possibly get a very important part of logics and possibly get as important as the classical logic, which at the moment connects all the logics together. Have I been clear? Yeah.
Sure.
Thank you.
Do you have to translate that into Italian?
Yeah.
I don't think I should translate it.
Yeah. Tenterò
Maybe, oh, he should say if he's right.
Vabbè, traduco io. Dunque, da quel poco che so che i progressi nella meccanica quantistica hanno portato dei cambiamenti anche nella logica e quindi la logica si è dovuta, diciamo, adattare a risolvere nuovi problemi come appunto quelli creati dalla meccanica quantistica, inventando nuove regole formali, se vogliamo. Per esempio c'è un modello appunto di logica cosiddetta quantistica che ha introdotto accanto ai valori vero o falso un valore indeterminato, anche questo non l'ho detto, no? Cioè, questo è un esempio di come appunto un problema fisico può influire anche sulla logica, e ho chiesto al professore se secondo lui un tale processo può avvenire anche in futuro, può diventare sempre più importante in modo tale che appunto una logica cosiddetta quantistica, come spesso viene chiamata, possa essere considerata della stessa importanza, la stessa stregua della logica classica, che normalmente ora collega le varie logiche. Questo è per quello che so, non è molto, comunque spero di
Well, my answer will be much shorter than the question, because I do not know classical logic, quantum logic. I have not studied such things. I'm sure that it should be valuable to develop these subjects in the light of what we understand in quantum mechanics. However, the basic problem is for the physicists who understand quantum mechanics to be able to appreciate the points of logic that you are mentioning. One is very, very formal, the other is more practical, and first that gap has to be bridged. Otherwise, I cannot say anything very concrete. I do not know this subject very well.
La mia traduzione sarà ancora più breve della risposta. Il professor Mukunda ha detto che la risposta è molto più breve della domanda. La traduzione sarà ancora più breve. Beh, essenzialmente lui non è un esperto di logica. Auspica, diciamo, che quelli che conoscono la meccanica quantistica possano effettivamente studiare e capire un po' meglio quello che succede. Visto che io sto parlando, diciamo, forse potrei rispondere io in parte a questa domanda. E il problema è che, così come la meccanica quantistica non può fare a meno della fisica classica, così la logica cosiddetta quantistica non può fare a meno della logica classica. E quindi ancora non è molto chiaro, diciamo, in che misura uno possa pensare di aver costruito una logica quantistica che sia indipendente dalla logica classica. E questo è ancora tutto da studiare, diciamo.
indipendente, equivalente, sostituibile.
No, c'è proprio questo, diciamo, la definizione di un sistema quantistico ha bisogno dell'esistenza di un osservatore classico. Allo stesso modo la cosa, diciamo, quello che succede normalmente è che uno cerca di creare un isomorfismo fra la logica classica e la meccanica classica, diciamo, e la logica quantistica e la meccanica quantistica. Beh, e così come la meccanica quantistica non può fare a meno della meccanica classica, la logica quantistica non può fare a meno della logica classica, e quindi in questo senso è difficile pensare a un superamento. Cioè significa che è necessario ripensare al tutto. Fra l'altro c'è un libro interessante di Beltrametti e Casinelli, uscito l'anno scorso, che è specificamente indirizzato a queste questioni ed è uscito per l'Enciclopedia delle Matematiche.
Yes, I have a question, maybe too much philosophical, but since you've spoken about unobservable entities, and you have talked about 3 ways of introducing them, or let's say
3 levels.
Well, the first seems to be unobjectable because the first kind, you seem to say that it may be easy to dispense with this kind of unobservables, and the third kind seems also unobjectable because you cannot object to the use of them because you say it's necessary to use them, otherwise we cannot have any experimental theory. But in the second type, this is what worries more philosophers. You say we use them because it's more convenient. And you have an example also from the theory of Mills and
Young and
Mills, which you say, well, maybe we could have another theory, but the complexity, the mathematical complexity of our model would increase very much. Of course, this is the ontological problem for philosophers, and it's the problem of on what there is, as Quine would put it, and so what is there, I ask you? Namely, should we believe to the ontology of physics, or sometimes just matter of convenience, and so elements of
convenience?
Yes, let's say sort of conventionalism motivates the introduction of these unobservable quantities. So there. So this is the.
So do you wish to translate that into Italian?
Il problema era il tipico problema ontologico, siccome il professore introduceva, parlava di 3 modi di introdurre quantità non osservabili in fisica. In una, la prima diceva banalmente possono essere eliminate, nella terza non ne possiamo fare a meno, ma nella seconda in qualche modo sono motivi di bellezza, di semplicità della teoria che allora il problema è diciamo il solito problema fra una visione convenzionalista o una visione realista delle teorie fisiche. Se sono semplicemente questi motivi, nel secondo caso se ne può mettere in luce qualcuno, allora c'è un punto di vista abbastanza convenzionalista in questo tipo di introduzione delle quantità non osservabili.
Yeah, I think you have asked a very important question. I cannot answer from the viewpoints of philosophy. I do not know those very well. But I can only tell you what I understand as a physicist. You could say that this second category is the conflict between reality and convenience. The truth of the matter is there is another physical concept which is relevant to answer this question, which I referred to briefly, the concept of local actions. Now, the simplest example is in relativistic classical electrodynamics. There is the theory of Wheeler and Feynman, in which one tries to describe a theory of charged particles all by themselves without introducing an electromagnetic field. You're probably familiar with this. What happens in any such description is that you must imagine that the electric charges interact with each other even when they are far apart. Okay. Now, for many purposes, as far as I understand, such a description gives the same results as a description in which local fields are introduced. What is the physical difference between using and not using a field? In the Wheeler-Feynman description or other similar theories, an electron here is able to interact, exchange energy and momentum directly with an electron far away. If you have fields, the principle is that the electron responds only to the fields just where it is and near it. The field has its own laws of propagation. Then it will go and hit another electron. Now, physicists feel much more comfortable I agree there is no answer that I can give to your question, but from a practical point of view, they feel it is much more correct and natural that there should be only local actions. Okay? Now, on this very question, there are apparently differences of opinion. Some people say, obviously there are physical effects which we have measured, which show you that the electromagnetic field is real, that you cannot do without it. In other words, some people say, there are effects which we have measured which show you that a theory of the Wheeler-Feynman kind cannot explain those results. There are such people. Other people say, you have not tried hard enough. We will show you how to explain vacuum polarization without introducing the electromagnetic field. I am not an expert in those areas, but I just want to tell you there are both points of view and it's not a settled matter. Okay?
No, this is very, I have not understood quite well whether the two descriptions predict the same sets of consequences that can be checked with an experiment, or one is stronger or more powerful than the other. In that case, I do not see.
There is no definite answer at the moment because there are claims in both directions in the literature, which only goes to show that the subject is still alive and developing. But the concept of local action is so important. One describes general relativity. Wigner uses this description. General relativity is the ultimate expression of existence of only local actions. Okay, you have complete freedom to change your description of phenomena in one region of space-time, independent of what is going on elsewhere. Every interaction should be by contact. Even in this context, as far as I know, there is a work of Hoyle and Narlikar, which tries to imitate the Wheeler-Feynman approach for relativity also. So, I'm afraid the question is not closed, and it is the most important of the three categories, as you have recognized. And I cannot answer any better.
La risposta dal punto di vista della filosofia, il professor Mukunda non si considera un filosofo, quindi non è in grado di rispondere. Dal punto di vista della fisica, invece, uno può dire che ci sono degli aspetti in questo diverso approccio. E il problema è essenzialmente quello che i fisici conoscono come teoria locale e teorie non locali. Ora, la località ovviamente è dopo la scoperta dei campi, è un concetto molto caro ai fisici, diciamo. E l'usuale argomentazione è che se voi avete due particelle, o comunque se fate qualcosa qua, è difficile che influenzi quello che succede dietro la Luna, diciamo. Ora, però questo modo di dire, diciamo, che sembrerebbe banalizzare la questione, non va preso letteralmente, perché ci sono teorie non locali, cioè uno può fare l'elettromagnetismo in una maniera cosiddetta non locale, in cui il concetto di campo non interviene mai. Cioè, ci sono semplicemente delle particelle e uno fa una teoria completa senza dover mai far intervenire la nozione di campo. Ora, quindi non si possono paragonare semplicemente in base ai risultati. Infatti si può argomentare in un senso e nell'altro. Bisogna perfino dire che andiamo in un campo della sperimentazione in cui l'interpretazione degli esperimenti stessi ha bisogno della teoria. Quindi la questione diventa particolarmente complicata. Ed è vero, in un certo senso la questione non può essere considerata chiusa, cioè il problema, uno deve preferire delle teorie che utilizzano soltanto concetti locali, anche se introducono concetti non osservabili, oppure facciamo, pur di non introdurre delle grandezze non osservabili, ci costringiamo a lavorare con teorie non locali indipendentemente dalla complessità. Non c'è nessuna risposta, infatti, diciamo, perfino la teoria della relatività, che è una teoria locale per eccellenza, in questo momento ci sono dei tentativi per metterla in un contesto non locale. Quindi la questione è da considerarsi aperta, diciamo. Altre domande? Well, I think we thank you very much and
It has been a pleasure.